I am overlooking the Long Valley Caldera just outside of Mammoth Lakes, California. Now, it's kind of hard to tell that there's even a volcano located right behind me, right? Well, let's zoom out and look from above. Okay, how about now? Can you see it? Now, just behind me, we can see part of the caldera that formed after the huge eruption that happened about 760,000 years ago. Now, this oval-shaped caldera is about 20 miles long and about 10 miles wide. Now, we know that it's a caldera, a really big one in fact. So what type of eruption caused this caldera to form? Do you think a non-explosive eruption or a really explosive eruption? That's right. This caldera was formed from a very, very big explosive eruption. In fact, about 650 cubic kilometers of magma was erupted explosively during the collapse of the caldera forming eruption. Now, 650 cubic kilometers of magma, let's think of that in terms that we can relate to. So that's about the same volume as covering the entire state of California in 4 to 5 feet of erupted material. So this yardstick is about 3 feet tall. Now 4 feet would be to here, and 5 feet would be to here. Almost as tall as me. I'm about 5 feet and 1 inch. So about as tall as I am of erupted material covering the entire state of California. Now that's a lot of material. And the caldera that was left behind just after the eruption, the hole was about 2,500 feet deep. That's a really big hole, and it had no outlet. So, over time, a caldera lake was formed in the big caldera hole. And this happened over the course of about 600,000 years for this lake to form. And just about 150,000 years ago, the lake level rose so high that it spilled over the caldera and it rushed down the only outlet it could find, which happened to be the Owens River Gorge, what we know the Owens River Gorge is today. So the Owens River Gorge was cut by the overspilling of the caldera lake that rushed down to Bishop, California. And in fact, Crowley Lake, right behind me, is the leftover caldera lake. How cool is that? So what do you think was erupted? Do you think the magma had less crystals and bubbles, which formed a slow-moving lava flow, kind of like that maple syrup demonstration we saw earlier? Or do you think the magma had lots of crystals and lots of bubbles, causing the magma to rip apart as it was erupted, forming a fast-moving pyroclastic flow, similar to that soda demonstration? Yeah, you're right. This is a very explosive eruption, which means that the magma had a lot of bubbles in it, or gas. So when the eruption occurred, it was extremely explosive and ripped apart that magma, forming an ash cloud that went up about 10 kilometers high in the sky and then later collapsed, forming pyroclastic flow deposits going on all directions within the caldera. So, what happened to all that magma and the pyroclastic flow deposits that were erupted? Well, that's a great question. Since the pyroclastic flow deposit collapsed and stretched out across the caldera in all directions, it also kind of filled in that huge hole, that 2,500 feet deep hole caldera that we talked about earlier. So, about half of the total erupted material was trapped within the sunken depression or the caldera. What about the rest of it? Well, about a third of the pyroclastic flow deposit flowed out in all directions, forming the Bishop Tuff. This is the pyroclastic flow deposit that we refer to from this caldera forming eruption at the Long Valley Caldera, the Bishop Tuff. And the Bishop Tuff blanketed the whole landscape and covered everything in its path. There were no more gorges, there were no more river valleys, there were no more mountain ridges. It covered everything in its path, and we'll show an example of it in our next stop. Now, a sixth of the erupted material was dispersed across the North American continent. And the way it's dispersed is because it's composed of small ash particles. Now, ash is smaller than a sand-sized particle, smaller than what I'm holding in my hand right now. And it's made of volcanic glass, and it's easily transported through wind patterns. So it traveled across North America and is dispersed as far as Kansas and beyond. Now we'll see an example of that on our other stop that we'll see. Now the Bishop Tuff blanketed about twice the area that's exposed today, and it stretched across as far as the Mono Basin up north and as far south as Big Pine. Now today, it's either buried or has been transported or eroded away over time. Okay, let's go look at the Bishop Tuff in more detail and other materials that were erupted so that we can investigate more and more about this eruption. Let's go. Welcome to the Owens River Gorge. Here we can see inside the layers of the Bishop Tuff, and I'm standing on some boulders of the Bishop Tuff right here as well. So what is tuff? Well, tuff is a type of rock that's formed from a pyroclastic flow. When the pyroclastic flow deposit is so hot, it fuses the individual ash particles that's composed of volcanic glass. They're fused together, which we call welded. So the Bishop Tuff is a welded tuff. And that just shows how hot this flow was when it was deposited. Now, there's some other rocks that we could find within the Bishop Tuff, and they're called pumice. Has anyone heard of pumice before? Well, pumice is a type of volcanic rock that's formed during very explosive eruptions, like the Long Valley Caldera eruption forming the Bishop Tuff. And pumice is made primarily of volcanic glass that's welded together, but has individual holes throughout the rock, and it's made up mostly of gas. So when it's erupted, the gas escapes, and you're left with a frothy, very light rock. Now within the Bishop Tuff, there's also a lot of rock fragments that have been picked up along the way when this flow is moving across the ground surface. And the rock fragments can be all different rock types. It depends on where you're located from the caldera, which is really cool to think about. So when the eruption occurred, it exploded the surface of the ground where the caldera formed, and it incorporated the previous rock that was there into the pyroclastic flow. So here we're on the south end of the caldera, and we see a lot of these black inclusions of these rock fragments, and they're thought to be a type of mudstone that's commonly found up near Mount Morrison near Convict Lake. So that just shows the power of this caldera, where it ripped apart the ground surface and then carried that rock that it ripped up down through the flow towards Bishop, which is right behind me. So depending on where you're located near the Caldera, you'll find different rock fragments within the Bishop Tuff. So here we have mudstones. Up north you might have granite pieces within the Bishop Tuff, and you might find some quartzite too. Now let's take a closer look at this Bishop Tuff. We can use our observations that we make as clues to investigate even more detail about this eruption. So let's get started. Now one observation that I make is the color of the rock itself. It's kind of a pink orangish color. And the black that you see is a form of lichen. And here are some examples of the pumice that we find within the Bishop Tuff. So these are individual pumice fragments that, similar to these rock fragments, got picked up along the way as this pyroclastic flow is moving across the landscape. And it picked up anything in its path and included it within the pyroclastic flow deposit, which solidified into this Bishop Tuff. We're at the toe end of the Bishop Tuff. Now remember, we talked about the full extent, or how far the Bishop Tuff traveled when it was first erupted. And it's thought that it traveled all the way down to Big Pine, past Bishop, which is just south of us right here. And over time, the Bishop Tuff has eroded or been transported away through different forces like glacial activity, rivers, wind, you name it. This eruption happened about 760,000 years ago. So a lot of changes have occurred since then. But today, this is the location of the toe of the Bishop Tuff. And as you can see in front of me, and also right behind me as well, is the greatest example of the ash flow layers that are accessible to us here. And this is the Chalk Bluff Road, and you drive right past this layer, these layers of the ash flow, and we're going to take a closer look at them. So ash, volcanic ash, is smaller than the size of a sand particle. So here I have it broken up into smaller pieces, and as you can see, it just kind of leaves behind this fine dust. And this fine dust can be transported very far distances through wind and air transportation. Great job, geologists! So now that we've discovered more and more about this volcano and the super eruption that occurred about 760,000 years ago, we can use our observations to think about how this eruption and other eruptions similar to this one impacts nearby communities, like the one right behind me, the town of Mammoth Lakes. So volcanoes are very dangerous, and geologists monitor the volcano's activity daily. The volcano's been sleeping for some time now, and if it ever decides to wake up, which likely won't occur in our lifetime, they have safety measures to alert the public and plans to keep everyone safe. For more information, you can go to the California Volcano Observatory website, which I'll provide a link to. So some very positive impacts on the community that we have today are geothermal energy, and located right behind me is the Casa Diablo Hot Springs and Geothermal Facility, and it's located just outside of Mammoth Lakes. So this power plant taps into the Long Valley hydrothermal system. What does hydrothermal mean? That's another great question. Well, hydro means water, thermal thermal means temperature. So it's hot water that's located underground, not too deep, around our water table level. And the thermal energy from that hot water can be transferred to drive generators that produce power. How cool is that? And the power plant behind me produces enough energy to power over 40,000 homes in the Eastern Sierra. So if you live in the Eastern Sierra, your power likely comes from the hydrothermal system of the Long Valley Caldera. Some other positive impacts to the community of this volcano are hot springs. I mean, who doesn't love nature's hot tubs, right? And there's many hot springs that are all natural throughout the Eastern Sierra, and that has to do with the Long Valley hydrothermal system. Another positive impact to the community are rich soils. So when volcanic ash mixes with soil, it provides a lot of nutrients, and these nutrients are great for farming and producing a really nice crop system here in the Eastern Sierra. So some really great positive impacts on the community. Yes, volcanoes are dangerous, but when they're sleeping, they can provide great positive impacts to our community.